Okay, so today we'll look into more problems on frame. Um, now, let's look at this problem in the middle. Okay, uh, so we have this frame comprising of three components, and two of them are making two sides uh, of A, and then there is this central line CF. Okay, now we have seen that we can take individual components and draw the free body diagram for them, and then we can write the equations of equilibrium for individual rigid bodies. Okay, but what if we try to write the the equations of equilibrium, or what if we drew the free body diagram for the entire structure? So if I take this entire structure, because this whole structure must also be in equilibrium. So if I look at it at component wise, where I'm looking at individual rigid bodies, they are also in equilibrium, and also the entire structure is in equilibrium. Okay, so I can write equations of equilibrium for this whole structure. Now for that I need the free body diagram for this structure. Okay, now if I were to draw, let's say, the free body diagram of GD, this member right here, I'd be showing forces coming from this pin joint E over here. So in this drawing, all the joints are pin joints. So this joint E over here and D over here. Okay, but when I'm or if I were to draw the free body diagram of this horizontal member, which is CF, then also I'll be showing the forces coming from B and E. But since I'm drawing the free body diagram of the whole structure, okay, that means the actions and reactions at E combine, okay, and they essentially doesn't show up in the free body diagram of the whole structure. For example, if you think of the two members CF and DG, okay, both are connected at E, and they are receiving forces from one another at E. And but if I consider the whole structure, these two forces are actions and reactions, which means they are equal and opposite and acting at the same location. And for the whole structure, therefore, we don't need to show that force. Okay, so when I'm drawing the free body diagram of the whole structure, this is how it would look like. So there is this 600 Newton force, and this is a couple moment, so it doesn't matter where do I show it. So 120 Newton meter of couple moment. Okay, and yes, I should be showing all the dimensions as well, but let's try that. So from here to here, it is a 60-degree angle. Okay, so this angle is 60 degree, and this is 200 millimeter, this is 400 millimeters, and this is 200 millimeters. Okay, we do not need the vertical distances as it seems, because we can figure them out from the horizontal ones. So C to B is 300, then E to F is also 300. Okay, so you are receiving forces at C and F. Now let's draw the free body diagram. I mean, let's draw the reaction forces coming from the supports at A and G. A right here is a roller support. Okay, that means A A can only prevent motion normal to the plane, but in absence of G, okay, this entire structure, without changing its orientation, okay, can also slide and slide along the plane. Also, the entire structure could perform rotation about A. Okay, so that means A doesn't provide any reaction moment. That is, it doesn't constrain any rotation in absence of G. Neither does it constrain any horizontal motion. Yes?
Sir, one of our friends are waiting.
Okay. Okay. So at A, we can expect AY, and since G is a pin joint, so we can expect GY and GX. Okay. Now, since we are not talking about the joints B and E, because we cannot, because when we consider the total structure, the forces from B and E are internal forces and they cancel out. So we are only left with three unknowns: AY, GY, and GX. Okay, and then we can figure out, or rather, those we can figure out, okay, by writing the equations of equilibrium for the entire structure. Okay, so can you write, or can you represent this whole system into an equivalent force system? Okay, to a convenient point, and then determine the reaction forces and the moments. There are no reaction moment. So can you figure out the reaction forces? Okay, so all I'm asking you to do is
Sir,
to yes.
sir, I have one doubt. There are B, E, and D point, and there should be some force also.
At
I
point
mean,
B and E,
reaction forces.
at
Yes, sir, they
B
are
and
pin joint.
yes, they are pin joints. The
So there should be
from
some reaction
okay,
forces.
okay. So can I talk? Are you talking about the points B, E, and D? Are you talking about the points B, E, and D?
Yes, sir.
Can
Yes.
you just, okay. So actually, that is what I have been. I don't know whether you joined late or not. That's what I have been talking about. Now think of the member CF. Okay. And I'm not drawing the complete free body diagram, but let's say it receives some EX and EY. Okay. At E. But who provides that? Of course, the member DG provides that. So let's take DG, and at E, then it must be receiving the reaction of these two forces, which is negative EY and negative EX. When you are drawing the free body diagram of the whole structure, these two actually combine. Okay, because when you are drawing the free body diagram of the entire structure, you are not considering the two objects to be different. You are considering the total assembly as a single unit. Okay, for example, let's take this rod right here, okay, hanging due to its own weight. Okay. So if I am being asked to draw the free body diagram of the rod, I'll be showing a center of gravity, the weight coming from there, and then the reaction it is receiving from the support. And since at the support it's a fixed joint, so I'll be showing Ry, Rx, and some moment reaction. Okay. But eventually, when I solve the equations of equilibrium, these two quantities would be 0. Okay. But let's say if I am trying to draw the free body diagram only up to this part of the bar, so then I have this weight of this delta x part of the bar, so weight of this delta x part, and the force it is receiving from the upper portion of the rod. Okay, I can imagine this rod consisting of several coin-like structures, okay, or disc-like structures, which is eventually makes this cylinder. Okay, so here I'd be receiving some other what should I call it, reaction force right here. Okay, but who is providing this reaction force? Now if I draw the free body diagram of the top half, then I have this Ry, Rx, and this reaction moment, and this Q is being applied to the this upper body, okay, by this lower body. Okay, in your mind you might be thinking, why am I putting Q? It should be the weight of the lower portion of the geometry. Yes, but that comes from the equations of equilibrium of the first body, I mean the first half of the body. In addition to that, the weight of this upper half, WL minus delta x, is also acting on the upper half. Now when I'm drawing the free body diagram of the whole structure, okay, now this is not something that has been introduced to you, drawing the free body diagram of a portion of a geometry. Okay, but you can think of this individual links are like portions of this assembly, and you have already drawn the free body diagram for such portions. Okay, but if you combine these two, you will get the free body diagram of the whole structure. And when you do combine, and this is where it counters your understanding of action and reaction, that action and reaction do not act on the same body, they do not cancel one another. But you see, when I'm drawing the free body diagram of two bodies, or portions of a single body combined as a whole, okay, then I have no place to show those actions and reactions, because there would be plus quantities and the minus quantities, which would eventually cancel themselves and not be appearing in this drawing, in this free body diagram. Does this make sense now?
Yes, sir, I have understood.
Okay, so there is a positive and a negative pair. I don't care which one do you want to call positive. Okay, and of course they are not acting on the same body. Okay, but when you consider the assembly or the structure itself, okay, so there are quantities with plus sign and the same quantities with a negative sign. Okay, so eventually the net resultant right here at E would be 0 as far as the assembly goes. Okay, now my question is that for this entire structure, okay, you can write 3 equations of equilibrium. That means basically you can reduce it to an equivalent force system, which will have three components, two force components and a moment component. And for equilibrium, all those components are zero. So you have two force equations and one moment equations, known as the equations of equilibrium. And by setting those equations of equilibrium to zero, you can solve for ay, gy, and gx, right? So has anyone already solved it?
Sir,
Yes,
while solving it, sir, all these 200, 400, these are in millimeters.
all of these are millimeters. When the unit is
Okay,
not given, it's always millimeters.
okay, sir. Sure, sure. 720 plus 85. That's
For example, if I write uh, moment in moment about z axis with respect to point G right here, so I'm going to get uh, this counterclockwise moment 120, and then the clockwise moments, which is 200 plus 400 plus 200, that is 0.8 times ay, and then the 600 Newton force acting 100 millimeters in positive x as compared to G. So you see over here in this problem, the coordinate origin is also placed at G. So 0.1 times 600. So therefore, ay equals 60 divided by 0.8, which is, I guess, 75 Newton.
Yes, sir.
Okay. So once you have that, you can actually write the other equations of equilibrium. Summation of all the forces in x should be 0. Summation of all the forces in y should be 0. And I don't see any force in, sigma fx equals 0, which basically means there is only one component of force that is in x direction, which is gx, and that goes to 0. Am I correct? There is only one component of force in x as far as the whole structure is concerned. Then if y is ay plus gy minus 600, so gy turns out to be 525 Newton. Is that so?
Yes, sir.
Yes, sir.
Okay. So by writing these equations of equilibrium, I can get the values of the reaction forces. Okay. So I need you to note a couple of things here. First thing is, let's try to answer this question. So, does this make equation count higher by 3? So, for example, in this case, there were 3 rigid bodies involved. Okay. So, the question is, does this make 9 plus 3, 12 equations of equilibrium? Because you see, if I were to write down all possible reaction forces irrespective of their direction, so there was Gx, Gy, and would you believe both the components of dx and dy, then bx and by, ex and ey, and ay. These are the only set of unknowns. Now, how much is the count of number of unknowns? It means if I in this question, if I'm asked to find out what are the reaction forces at every point, okay, which is A, B, E, D, G. Okay, if I ask you what are the reaction forces at every location, so how many unknowns? So that is the most generalized question that I can ask over here. And in that sense, how many unknowns are we talking about? So all of these joints are pin joint except for A, which is a roller support. So only one reaction coming from A. For all others, there are 2, which basically means a total of 9 unknowns, right? Okay. But does that mean the equations that I'm getting by drawing the free body diagram of the whole structure, okay, gives me additional 3 equations? The answer is this. Answer is yes and also no. Yes, that gives me 3 additional equations. Okay. And yes, that has advantages. Okay. What are the advantages? You are not solving, okay, a system of 9 equations versus a smaller system of 3 equations. For example, in this problem statement, if I were to ask you what are the ground reactions, what are the reactions from the supports at the ground, that is at A and G, that you can answer simply by solving the simply by drawing the free body diagram of the whole structure and writing the corresponding set of equations of equilibrium. Okay. And for that, you don't have to write any further equations of equilibrium. Now, why did I say no? It's because, yes, I do get 3 additional equations, but 3 equations are not linearly independent. They are not linearly independent, which means they are linearly dependent on the other 9. That means these 3 additional equations that I am getting, okay, they are not linearly independent when combined with other 9 equations. Actually, they can be formed by other 9 equations. Okay, that means if you would draw the free body diagram of individual rigid bodies and then write their corresponding equations of equilibrium, those equations of equilibrium can be combined to form the equations of equilibrium of the whole structure. So although I get three very different looking equations of equilibrium, they are not linearly independent from this 9 equations. Actually, they can be found by this nine equations. These 3 equations can be formed by these 9 equations. The point is, in the end, I have a total of 9 linearly independent equations and 9 unknowns to solve for. Okay, so the system is consistent. Okay, and if that were not the case, I'll not be able to solve this equilibrium problem right here. For example, instead of using a roller support, okay, instead of using a roller support at A, if that were to be changed with a pin joint, at A, okay, that would give me an additional reaction force at A, okay, which I cannot solve from this set of equations. That means then I'll be having total 9 unknowns, and therefore some of them cannot be, at least some of them cannot be calculated from the equations of equilibrium. Okay. For example, I can definitely calculate AY by taking the moment about G and setting that to 0. So all I'm saying is that some of the components of the forces cannot be calculated. AX and GX cannot be calculated. Okay, we know that AX is minus GX from this equation. I will get another AX. Okay, so in that situation, if I were to put a pin joint instead of the roller, okay, this problem would become something called statically indeterminate. That means you cannot figure out all the reaction forces or all the forces in this problem or moments, okay, simply by solving equations of equilibrium. But does that mean statically indeterminate problems cannot be solved? The answer is no. The statically indeterminate problems can be solved, but they can be solved only for deformable bodies, not for rigid bodies, number one. And they can be solved, okay, not just from the equations of equilibrium. When you combine the equations of equilibrium with equations of deformation, okay, that is involving stress and strain and deformation and so on. So in the end, satisfying so and so condition that this is not deforming, the deformation here is so much. Okay, so from that, eventually the values can be obtained, but the thing is, they cannot be solved from the equations of equilibrium. And since you are dealing with only rigid bodies in this course, so you don't have the access to those equations that can lead you to the solution of the statically indeterminate problems. So you are so in a single sentence, you will not be able to solve statically indeterminate problems with the set of equations that you learn in this course, that is the equations of equilibrium. Okay. One more thing. So statically indeterminate problems or SI problems are because of the result of over constraint. And there is also such thing called under constraint. For example, instead of having a pin joint at G, if I were to have a roller support at G, okay, so that would give me one less reaction force. Gx should be 0 trivially, but then that problem would be considered under constraint, although none of the external forces has an X component. Okay, but let's say there were one force that was acting at D, external force, which had an X component. So if G was a roller support in association with A, which is also a roller support, that horizontal force cannot be supported. Okay, so that would mean this structure cannot be in equilibrium in presence of a horizontally applied external force, which would make the structure under constraint. It is not constrained enough to be in equilibrium. Okay, so under constraint is just the opposite situation of over constraint. In over constraint, you have more unknowns. A 10th unknown will come, and you only have 9 linearly independent equations. So you cannot solve for all the 10. You can only solve for a few. Under constraint is a different situation, where under constraint is a different situation where there would be lesser number of unknowns, okay, and having more equations. Okay, so you see, we solve this set of equations with the understanding that there is equilibrium. Okay, in the premise of equilibrium, we solve this set of equations. Okay, but having an under constraint system, lesser number of unknowns and higher number of equations, okay, would render the system inconsistent, which would basically mean that our very premise that the structure is in equilibrium, that could be invalidated, okay, with under constraint situation. So we would not be able to solve the over constraint and under constraint problems, and we would always be given optimally constrained problems. So we would always expect to encounter only optimally constrained problems. That means requiring only the exact amount of constraints or the minimum number of constraints for the structure to be in equilibrium. That is optimally constrained problems. I would like you to focus on, let's say, the problem number, the next problem. Okay, so in this problem, okay, you see both the joints A and C are pin joints. That means you are receiving 2 unknowns from over here and another 2 unknowns from C over here. So a total of 4 unknowns. Okay, or sorry, 4 reaction forces coming from the ground, and that is making this structure optimally constrained. Okay, much like this structure in the left, there also both the joints A and C are pin joints, and you are receiving 4 unknowns or 4 reaction forces from these 2. And also the first problem that we solved on frames, okay, that also had 2 pin joints applied to the structure. So why is in some cases having 3 support reactions is optimally constrained, and in other cases having 4 support reactions is optimally constrained? So I can show you that this one is optimally constrained. You see there are 3 pin joints, okay, and from each pin joint you can expect 2 unknown reactions. So a total of 6 unknown reactions, and there are 2 rigid bodies involved. Okay, Now you may choose to draw the free body diagram of the whole structure, okay, or you may choose to do it by individual rigid bodies. But in the end, you know that you can only have 6 linearly independent equations. You have 6 linearly independent equations and 6 unknowns. So you have the perfect system to solve for those unknowns, which means this system is also optimally constrained. And same applies over here. 3 pin joints, 6 unknowns, each rigid body, 3 equations, and that simply serves the purpose. Okay. So in the examples in the left and the right, having 2 pin joints with the ground makes the system optimally constrained. And in the middle figure, having 3 support reactions, that is 1 pin joint and a roller, makes the system optimally constrained. Why is this difference? Can you explain this?
Sir, can you repeat the question once?
Yes, I'll repeat the question. So I hope you understand. In the figure, this figure and the figure in the left, both of them have 2 pin joints with the ground. Okay, and we just showed that the number of equations and the number of unknowns match. Okay, for this configuration, and so it does for the central figure. Okay, but the central figure is not supported by 2 pin joints. One is a pin, another one is a roller, which accounts for 3 unknown reactions coming from the ground. Why is so the question is this: why is that in some cases having 4 unknown reactions from the ground makes the system optimally constrained, and in some cases having 3 unknown reactions from the ground makes the system optimally constrained? Optimally constrained is the situation where your number of linearly independent equations matches your number of unknowns. Okay, so that part I'm trying to answer.
Sir,
Yes.
sir, please show the question once again.
Sure.
Sir, in the part BC,
Which figure? Central figure?
No, sir, the rightmost.
Rightmost, okay.
Sir, if I think the part of BC, rigid body, then to have an equilibrium, the same and opposite force should apply at point B and C along the line BC.
Okay.
Then, sir, I can take the vector that F that is applying at point C, and then I can think that AX and AY is acting at point A. Then the variable will become 3. And the angle theta at which the force F is acting, we can find out by the proper dimensions of the
Okay, I'll tell you what you're essentially doing.
Okay, sir.
Yeah, you are using the understanding of a 2-force member and so on. So basically, you are in the process of solving those equations of equilibrium, and what you are essentially doing is substituting for some of the unknown reactions in some of the equations. So in the end, you are showing that the number of equations and number of variables match. That I don't have any problem with. You see, the total number of variables and total number of equations match, and you can always show it to be always reduce that system into 3 equations, three linearly independent equations and 3 unknowns, because you can substitute for all the others 3. Okay, but that's not what I'm concerned with. What I'm concerned with, what it what does it physically mean to have two pin joints in the left and the right figure, and to have a pin joint and a roller support in the central figure. Now I'm going to give you an explanation, and that I'm only doing because I'll have to cover few more things today. So just tell me if this makes sense. So for this, we'll bring in the concept of collapsible and rigid frames. Okay. Now consider this image right here, one in the left. Okay. That is the central figure. Okay. If I really think about it, you had three rigid bodies. You just pinned them at three locations. Now by pinning them at three locations, we know that the pin joints can prevent two translatory motions, but it cannot prevent rotation. Okay. So imagine if this is member number 1, this is member number 2, this is member number 3. In absence of member number 3, if I were to just fix one of the members, let's say member number 2, the member number 1 would have only 1 degree of freedom. It could only perform rotation about member 2. But when you take the third rigid body and you pin them with the other two, this is what happens. You see, now you have this triangle whose side lengths, I'm just calling about this triangle right here, whose side lengths L1, L2, and L3 you cannot change. Okay. And when you cannot change the side lengths of a triangle, okay, you cannot also change the underlying angles. So together these two makes this entire structure rigid. If individual components are also rigid, this entire structure becomes rigid when you take three of them and pin them at three different locations, taking two bodies at a time. Okay. You see, this is not very obvious. If I were to take 4 rigid bodies, okay, and pin them one after the other, okay, I'm just drawing them as lines, and these are the pin joints. That is not a rigid structure, because to define a quadrilateral, not only do you need 4 link lengths, you also need one of the angles. And actually this makes up for the 4-bar linkage, where by changing the angle of one of the links, you can also change the angle of the other side. Okay. So all those mechanisms that you might have heard about, the the crankshaft in a vehicle, okay, then the crank rocker mechanism, the crank slider mechanism, all of this is a extension of this understanding. So for a quadrilateral, even with the 4 side lengths to be fixed, you can still change the angle, but such is not the case with a triangle. You might recall that the 2 triangles can be shown to be identical by something called side method, which means if the 3 sides are same, okay, they are essentially the 2 identical triangles. That means also the angle should be same and the area should be same and so on. But such relationship doesn't happen. Such law doesn't exist for quadrilaterals, because you'll also have to specify an angle. Now when you have 3 rigid bodies, pinned like this, that itself, the assembly itself becomes a rigid body. And that makes a rigid frame. And a rigid frame is optimally supported. This part is important. A rigid frame is optimally supported when it is supported like a single rigid body. Now, a single rigid body in a two-dimensional space will have three motions, two translations, and one rotation, ux, uy, and theta z. Okay. So this entire frame is just like a single rigid body, and it also has two translations and one rotation. So I'll need to prevent those three, and then the structure is optimally constrained. If I put more constraint, it is over constrained, and then I cannot solve. Then it becomes statically indeterminate, and I cannot solve it. If it is under constraint, it is chances are it is not in equilibrium. So how do I make it optimally constrained? First of all, at G, I'll attach it with the ground with a pin joint. Okay, so it cannot move without changing its. It cannot freely move in X or Y. Now, only thing that is left is rotation. Now, let's see if it is trying to rotate in this direction. How do I prevent that? By providing a normal support. That means it cannot. So by providing a roller support or a normal support at A. So the third support at A essentially prevents the rotation. Okay. And this way the structure is optimally constrained. Now it cannot translate in X and Y or rotate. Okay. But again, you might be confused with the fact that the roller only prevents the structure from going in the downward direction at A, not in A upward direction. But you see that design is only based on the fact that if this body has a tendency of rotation, that will only try to bring A in the downward direction. That's why the support is only provided from the bottom, and it is only preventing the motion in the downward direction. So in the essence, in the end, the essence of A is to prevent the rotation. Okay, the third independent motion. Okay. That's why you need only three constraints from the ground to make the rigid frame optimally constrained. Now, with all those examples involving a 2-force member and a 3-force member, all the examples, and even these two, a 2-force member that is BC and a 3-force member that is AB, the 2-force member, let's say CB in the case A, and the 3-force member AB. See, in all those examples of frame, you have two pin joints. Why so? I just draw a general situation. This is what each of those frames look like without the support. Just two rigid bodies pinned somewhere. Now, this doesn't make a rigid frame. If I were to call this one as member 1 and this one as member 2, member 2 is not completely fixed with member 1, which basically means, of course, if I hold member 1 somehow, member 2 cannot fly away anywhere, but it can perform rotation about member 1. So to start with, this frame, when not constrained, didn't have 3 degrees of freedom. It also had a 4th degree of freedom. Okay, so it had all the 3 rigid body degrees of freedom. That means it could rigidly translate in X, rigidly translate in Y, and rigidly rotate about Z axis. But also there is this additional degree of freedom that member 2 can also rotate about member 1. I cannot show it on this graph because it's a relative motion. Okay, so there is another additional degree of freedom. That means there is one additional way than in which the motion of this structure frame could be described in absence of any kind of support. Now, if I provide a pin joint over here and a roller support over here, that only prevents 3 out of 4 of those degrees of freedom. So 1 degree of freedom still exists. Just to prevent that additional degree of freedom, we need an additional ground reaction, and that's why we change the roller support to a pin joint. Okay, and this type of frames are called collapsible frames. Now, when it comes to rigid frames, because ground only provides 3 reaction forces, we can determine all the 3 reaction forces, all the ground reactions, by drawing the free body diagram of the whole structure and by writing the equations of equilibrium of the whole structure. So 3 equations and 3 unknowns works very well. But when we are dealing with flexible or collapsible frames, we have 4 unknowns, 2 from here and another 2 from here. And therefore, we cannot solve all the unknowns, all the ground reactions completely just by drawing the free body diagram of the whole structure. So we do need to look into individual members for that. Of course, in the end, if I consider all the unknowns, all the reaction forces, for example, 2 just over here, okay, and all the linearly independent set of equations, the total number of equations and total number of unknowns match in both cases. But if I were to only draw the free body diagram of the whole structure, okay, then for a rigid frame, at one go, just by drawing the free body diagram of the whole structure and writing the equations of equilibrium for it, I can determine all the ground reactions, okay, without looking into individual components. Such thing I cannot do for a collapsible frame. Okay, so does this make any sense to you? Are you a bit confused?
Yes, sir. I have some confusion in the flexible structures. Can you repeat once?
Okay, so flexible structure not only has all the 3 rigid body degrees of freedom. I mean, not only just it can translate in 2 directions rigidly and rotate about z-axis rigidly, it can also have that flexible motion. That means the relative motion between the 2 links. So that is one additional degree of freedom. And while trying to keep the object in equilibrium, we will have to constrain all the possible degrees of freedom. And since it has 1 additional degree of freedom, I need 1 additional constraint. So therefore, I replace the roller support with a pin joint just to provide that additional constraint. Now is it clear?
Yes, sir. That means at the uppermost point, the body can rotate. And to prevent
Yes,
that rotation,
yes.
we are providing the pin joint.
No, I mean, you can physically think of it, right? If this one is a roller support with the ground, and I'm just drawing stick bodies, and for this other side, there was a roller, okay? Can this body be in equilibrium? For example, if I apply
Yes,
a
sir,
force,
I understood the part. The body can
And if I
translate along the x-axis.
it can only translate because there is a relative motion possible over here. So yes, it can translate along x-axis. So what we can do is we can replace this roller with a pin joint, and then such motion will no longer be possible.
So that means we have to put that amount of constraints means which is required to diminish all the degrees of freedom.
Yes. So the idea is an object can only be equilibrium. Let's say when it is a rigid, when you prevent all the rigid body degrees of freedom. Okay. And that applies to both rigid bodies and deformable bodies. A deformable body simply deforms, okay, but it can still be in equilibrium But for that, the condition is all the rigid body degrees of freedom must be prevented. And that's why we are dealing so much with rigid bodies. Although we have been repeatedly mentioning that the real life objects are deformable and so on, the study of rigid bodies is important because in the end, what matters is whether or not the rigid body degrees of freedoms are constrained. Now, when you are using multiple rigid bodies, then you get additional degrees of freedom, and those are, rigid body degrees of freedom, because the individual bodies are still rigid bodies. But you took two rigid bodies, so if when they were not connected, the two rigid bodies, each of them had 3 degrees of freedom, a total of 6 degrees of freedom on a plane. But then you connected them with a pin joint, so you took away 2 degrees of freedom by applying a pin joint between them. So now you are dealing with 4 degrees of freedom of the structure, if not constrained by the ground. Okay, so to have a structure which would be in equilibrium, the ground also must provide that remaining number of constraints, which is 4. Okay, and that is the story of a collapsible frame. When you have a rigid frame, then you need only only 3 constraints on a plane. And if you have to solve a 3D problem of equilibrium of a rigid body, so the number of constraints should be 6. Okay, so I'm not fully solving this problem, but you should go ahead and solve this entire problem, because if we wait for solving this one, we would not be able to show the other problems actually. Okay. So let's look at this problem involving this triangular slotted plate. Okay, and okay, and this other rigid body right here. Acha. Now, if not supported with the ground and the wall, okay, can you tell me how many degrees of freedom would this assembly or this frame have? How many degrees of freedom would this assembly have if not supported by the ground and the wall? Ground and the wall are the same unit, it's earth. Okay, but if not supported with the ground, how many degrees of freedom will this assembly of rigid bodies have?
4.
Sir, is the point E a rolling point or pin joint?
You don't have to think about roller right now. Okay, don't think about the roller joint, the pin joint at A and pin joint at D. Don't think about the ground support. When you are trying to answer this, okay, now think of that the assembly of the 2 rigid bodies, that is the member ABC and CDE or DCE. Okay, now this assembly can translate rigidly in X and Y and rotate about Z axis rigidly. But then, in addition to those rigid motions, okay, where the assembly moves like a rigid body, one member can have relative motion with the other. For example, the member DCE can have relative motions with respect to ABC, right? So how many relative motions can DCE have with respect to ABC?
2.
2, right? Because it can slide along that slotted line without changing orientation, and then it can also rotate about C. Okay, because it's a circular peg in a slotted arm. So if I look at the assembly, that is ABC and DCE, when not supported by ground, it has 5 degrees of freedom. 3 which are absolutely rigid if the entire structure could move like a rigid body, and 2 which are the relative motions of DCE with respect to ABC. So there are 5 degrees of freedom. Okay, and therefore you need 5 constraints coming from the ground just to keep the object in equilibrium under the action of external forces. For example, there is this 100 Newton force, which is an external load. In presence of any external load, okay, to keep the frame or the structure in equilibrium, you need 5 constraints. Can you point out where are those 5 constraints?
So two from two pin joints each and one from the roller joint.
Yes. So you get 2 constraints from A, 2 constraints from D, and then additional constraint from E. Okay. So you see, you need 5 constraints. It's not even 4. This time it needs 5. So here it is 5. On the picture above it, it is 4. And on the picture left to it, it is 3. So it would depend on how many degrees of freedom the structure had if it were not supported with the ground. Okay. So you need to prevent all of those degrees of freedom. Okay. So, so can you draw? So we'll now try to solve this problem right here. Okay. Can you draw the free body diagrams of the so you can see that you need to draw if I want to figure out even the ground reactions, I need to draw the free body diagrams of individual components. So in this problem, because it's a collapsible frame and with 2 additional degrees of freedom, so we'll only draw the free body diagrams of the individual components. So draw the free body diagram of the member ABC and DCE. Okay, so this is ABC. So this is the known force of 100 Newton that it is receiving. And since A is a pin joint, it would be receiving 2 unknown ground reactions, AY and AX. And that's why A is my convenient point for getting the equivalent force system. Now, can you tell me in which direction so this gap is 140 mm and this gap is 160 mm. Now, can you tell me in which direction does the reaction force of C act?
Sir, perpendicular to AC.
Perpendicular to AC, right? So okay, so this is your C force at C. Okay, so if I write sigma mz about A for this first body right here, okay, so of course there is this clockwise moment 100 times 0.14, then another clockwise moment, but this time C times what? So C is the force acting perpendicular to AC. Now, so the normal distance on the force is AC, right? Now, how much is AC? Okay, so that way we can directly figure out how much is C. Then we can use summation of all the forces in X, which is AX minus plus C times
Sir, the length of AC should be 0.12 square plus 0.16 square.
Why 0.12 square?
Because C is not at the edge. It is
Okay, okay,
actually
okay, 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 okay. Yes. Okay. So you can solve this set of equations to get the force. Okay. What I think that value of C should be negative. So you substitute that negative value for this positive C right here. How much did you get for C? Okay, 0.12 squared plus 0.16 squared, right? So that essentially is 0.2.
0.2.
And over here it is 0.6. And over here it is so how much is value of C?
Sir, 70.
70.
So minus 70.
Minus 70, right? If you take it this way, then minus 70. Now, you know that value of C is negative. That doesn't mean when you draw the free body diagram of the other component, okay, you simply switch the direction. You'll have to be consistent with the direction. So what I'm doing here is I'm drawing the free body diagram of DCE. So at D, I'll have dy and dx. At C, I would imagine the resultant force would be acting in the upward direction, which would mean that I'll show the individual components as Cy and Cx. Okay. Now both would be negative because I have obtained C as a negative value, but I'll still show it like this. And of course, some ground reaction from E. Okay. So these are the dimensions. So when I'm drawing the free body diagram of the member 2, let's say this is member 1 and this is member 2, the unknowns are the reaction from E and then the reactions from D. And C by that time would be a known quantity. The consistency of the free body diagram is a mandatory. Okay. If you have shown in your first diagram C like this, in the second diagram the C must look like this. Okay. But while substituting the value for Cx, you can go ahead and plug in the negative value. That is okay. Okay. For example, if I write the moment equation this time for the second body with respect to D, so that would be 0.12 Cx plus 0.2 E. that equals 0. And then I can also write the force equations for the second body, which is sigma fx is dx minus cx minus e equals 0, and fy is dy plus cy equals 0. So cx is 0.6 c, and cy is minus 0.8 c, corresponding to what how we have drawn it in the free body diagram. No, cy is actually plus 0.8, because this is how we are drawing it. So this is the plus cy and this is the plus cx. So these two should be consistent. Okay. So just check the consistency of your diagram. I mean, it is okay to show one of the force components in along positive x, the other in the negative axis. Okay. But maintain the consistency. That means whatever you show, okay. For example, sigma fy should be ay minus cy, and that's why I plugged in minus 0.8 c, because cy is 0.8 c. Okay, so cy is considered positive in the downward direction, so just be consistent with that. Okay, so if on the body ABC it is positive in the downward direction, in the member DCE it would be positive in the upward direction, and same thing happens to CX. Okay, so I guess in this way you can solve this problem. Have you got answers for some of them?
Yes, sir. So the normal reaction force at point E is coming at 25.2 Newton,
Okay,
and the dx is coming
is it
as
plus or minus?
it's a plus,
Okay,
and the dx is coming as minus 16.8.
so dx is positive.
So dx is coming as negative,
Minus 6 point.
minus 16.8,
Okay, Newton.
and
dy.
dy is coming as 56.
dy is coming to be positive. Okay, it should,
Yes,
because
sir.
cy and cx both are negative, right?
Yes, sir. Yes, sir.
And what about ax and ay? Is that so?
Yes, sir.
Okay. Okay, so let's move on to next problem.
AX is coming minus 42 Newton.
Ax is not minus 42. If you take ax to be of this direction, ax should be positive.
Oh, okay.
Depends on in which direction are you showing AX.
Yes.
You see AX plus C times 0.6 equals 0, but C is minus 70. So AX minus 42 equals 0, so AX is 42.
So I took it in opposite directions.
Okay. Okay, so let's move on to next problem. So this one, okay. So question here is that if I apply 80 Newton force at the handles, how much is the clamping force? How much is the clamping force for the object? Okay. So you see this block A right here. So this block is actually free to slide in this groove that is shown with broken lines. Okay. So it is free to slide in that slot. Okay. And if it is applying, let's say, some F gripping force, so it is getting that in reverse direction as a reaction. So this block A, what other force is it receiving? So it is also receiving some force AX and AY. From the member ABC. But you see there is a spring right there joining AE. In the problem statement, it has been mentioned that that spring is a weak spring. And for most purposes, the force due to that spring doesn't count. Okay. And the job of that spring is to bring the block back to its original position. That means to the right hand extreme side when there is no gripping force. So once we apply a certain gripping force, let's say 80 Newton. Okay. Sorry. Once we apply certain forces at the handles. Okay. So so the force that would be that the block A deals with, okay, the other forces, that is this F right here and AX and AY, they are all much higher compared to the spring force that is there. Okay, which basically means this AX and AY are practically coming from the member ABC. Very little is coming from spring, so mostly it is coming from ABC. So now if I draw the free body diagram, so the problem statement is to figure out this F right here. So if I draw the free body diagram of ABC, can you identify that BD is a two force member? Can you see that this BD is a two force member? Which basically means it is providing this force, okay, which is 15 plus 6.25, which is 21.25 in this direction, and this point is D, and horizontally this is 50 millimeters. Okay, so that will give you the direction of the force coming from BD. Of course, ABC is a three force member. The second force is at C. Acha, one more thing I forgot to mention. Because A is only allowed to slide on this bottom platform, it is not allowed to penetrate the platform. It would be receiving some normal forces as well. Okay. So together they are keeping the block A in equilibrium. So over here we will be showing AY in the downward direction, which is possibly the wrong direction, and AX, AX in negative X, which might as well be the wrong direction. Okay, so all of these forces keeping the object in equilibrium. And I believe D and C are just vertically, you know, it is C is just vertically above D, which basically means D is that point through which the forces at C and forces at B are passing, which basically means the resultant of the two force component at A must pass through D. So you can also utilize that idea, or you can simply use the equations of equilibrium. Okay, so write down now A right here, this block A right here, okay, is so tiny that you can
Sir,
treat it like one second. You can treat it like a particle, which basically means it has only two equations of equilibrium and not the third one. Okay. Yes, what were you asking?
sir, can you show the question?
Sure.
Yes, sir. The below the point D,
Hmm.
there is some 80 Newton force, and what is the significance of that force?
Okay, that 80 Newton force, you see, mm, that 80 Newton force is when you are, that is actually the, if you consider the equilibrium of the whole structure, that means that involves, the
So that means
that platform at the bottom. Okay, so that is only being subjected to 80 Newton and 80 Newton. Okay, from the let's say the hand forces. Okay, and then the other set of forces, let's say it is gripping a piece of wood between its vices. So at the two vices it would be receiving F and minus F. Okay, so that would complete the free body diagram of the entire assembly. But here we are only bothered about um, let's say the gripping force, that is the force F that A receives. Okay, so what we are doing essentially is only taking parts of it. Yes, what is your question?
so my question was why the below 80 Newton force is applied. Sir, is that just to prevent the translation along the y direction of the whole body?
Yes, I mean, if you are, trying to grip a piece of wood with this kind of instrument, okay, or this kind of device, so you'd essentially be putting two 80 Newton forces on the two sides, right? That's how you grip it.
Yes, sir. Yes, sir. I am clear now.
It's actually no different than a tongue. Okay, it looks different, but it is no different than this figure right here. You see, when the values of the force are same, 80 Newton force. Okay, although this problem is a lot simpler. Okay, so so once you write down the equations of equilibrium and eventually solve them, you can actually get the value of the gripping force right there. Okay, and I'll actually leave all of these problems. Okay, actually, if possible, you can take a screenshot of all of these problems. Can you see all the images?
Yes, sir.
Okay, so take a screenshot and you can try to solve all of these problems. I'm just going to briefly discuss, because if we try to solve them in the class, we would probably run out of time. Okay, so we have covered mostly all the problems except for two. Uh, okay, so on the top row, the middle figure is currently we are talking about. Okay, so so in this case, we are actually so in this case, we are actually trying to figure out the gripping force at A. Okay, and mostly we have drawn the free body diagram, and from those free body diagrams, if you write the equations of equilibrium, you can very easily solve this problem. Okay, it's not a very difficult problem. Achha. Now, now if you have taken screenshot, then we can go back to the discussion of the other two problems. Now you see this this wire cutter in the right. Okay, that actually is made of four three-fourths members. And these are the members G, F, D, then G, F, C. G is where the wire is being cut. Number 3, E, C,
Sir, can you please zoom it the figure?
yeah, sure. ECA is a third member, and number 4 is EDB. Okay, so EDB is your E is this pin joint. Okay, in the middle. Okay, so for example, you can take the member. So this 20 Newton forces you are applying at the handle, and how much force is being used to cut the wire. Okay, so if I drew the free body diagram of this member, this problem might look complicated, but it's actually not. Okay, so there is C, there is F, and there is G. Where some cutting force so the plane on which the wire rests, so this is the plane, and that's where the cutting force would be applied. Okay. But if you look carefully, that plane is actually parallel to the center of the wear. The center of the wear joining and if being joined. So that line, and that line has kind of this slope. If you were to show the center of the wear, that is at 36 millimeters from F horizontally, and vertically this location, that means where the center of the wear should be, is 10 millimeters. That actually should give you the direction of this force, cutting force F right here. Okay. Let's call it something else. Let's call it P being applied for cutting. Okay. Now at AF, you can expect there is, because it's a pin joint, you can expect Fx and Fy. At C, you can expect Cx and Cy. Four unknowns, right? So you have four unknowns and three equations of equilibrium. Now if I draw the free body diagram, of this other component, that is ECA. So at A, it is receiving forces EY and EX, and at C, it is receiving negative of this Cy and Cx. Okay. So again, you see there are four unknowns, but that doesn't make up for 8 unknowns, because Cx and Cy appear in both. So that only is 6 unknowns, okay, which you can solve from this set of equations. Okay. Now, along with all the x components, x coordinates of the points, okay, the y coordinates are also important. For example, if you look carefully, the point C is 10 plus 9, 19 millimeters above E. So from E to G, that is 10 millimeters. From G to C, that is another 9 millimeters. Okay. So all those components are important. So between F and C, it is 25 plus 21, total of 46. Okay. Between E and C, that is only 21. And between C and A horizontally, that is 88. Of course, you do not need the y coordinate of A, because the force at A is vertical. See, all the dimensions are there only to calculate moment. Okay. So I believe with this set of free body diagram, you should be in a position to get. So of course, you need to resolve P into components, right? P into X and Y components, and that you can do by using these two dimensions, 10 and 36. Okay. Because the line G, so G is at that height from F, okay, and this plane of the shank of the cutter, okay, is actually parallel to the line GF, and force P would actually be normal to that shank. Okay, so in a way that would be normal to the line GF. So once you know the direction of GF, okay, you can get the direction of P. Okay, so that's why P is a single unknown.
Sir,
Yes.
sir, if I think about the first diagram,
Mm-hmm.
then P and Fx, Fy, and Cx, Cy all are unknowns.
Mm-hmm. So
And in
you are
the
saying that there are total 7 unknowns?
yes, sir.
Okay, that's what I was also thinking. So then the only option is to go for the other two links as well. You see, that's what I was counting. Uh,
Sir,
there are,
sir,
yeah, 1 second, just 1 second. So there are 4 rigid bodies involved. Okay, so there are 12 degrees of freedom. Now there are 4 pin joints which take away 8 degrees of freedom. So, and then this wire is preventing from the scissor or this cutter to close. So that is the 9th constraint. Okay, but you see, in this for this entire structure, we are not bothered about how this entire structure, okay, can rigidly translate or rotate. That means, it's not that the cutter must be held in this position. It could be translated into other location and it can still cut the wire, or it could rotate and still cut the wire rigidly, of course. Okay, so that's why we are only seeing 9 unknowns over here, although we could write 12 equations of equilibrium. Yes, you are saying something.
sir, I was saying that if I think about the part EC only.
Only EC.
Yes,
What?
sir.
There is ECA.
Sir, is the it is the whole body. Like in the case, I was thinking that if I think that EC is a part, only, then
No,
I can think about
no,
that is a two force member.
no,
Is it
EC is not,
attached with the whole body?
yes, ECA is a single body.
Then with that part we are attaching the FC part.
Yes. So so there is this. You see, it's again of 4-bar linkage. Okay. So there is this point is E, this point is C, this point is F, and then this point is D. It's just that in this drawing, the point E is somewhere over here. Okay. So this is a 4-bar linkage, which basically means this system has only, I mean, this is not a rigid structure. In addition to rigid body degrees of freedom, which are like 3 degrees of freedom, it also has 1 degree of freedom. That means the angle between these two ends can change. Okay. And and what happens when these triangles change, as happens with every scissor and every wire cutter and every tong. Okay, it is trying to grip or cut something. Okay, but when you place something to cut, that offers a resistance against cutting, and actually this rotation degree of freedom is prevented. So in the end, the entire structure will have only the 3 rigid body degrees of freedom. That's why you have 9 unknowns involved in this problem. Okay. I thought by considering only one side of the problem, I will be able to solve this, because it turns out that there are 7 unknowns and 6 equations. So possibly we'll have to consider the other half as well. Okay. So, take this problem as an assignment, try on your own, and if it still doesn't solve, by taking free body diagrams of the 4 components and then applying all the equations of equilibrium and on. Okay, so then we'll try to discuss
Sir,
this.
it will be very much impossible, because there are 7 unknowns and 7 variables, and a lot of equations will be there. Then it will be very much impossible for solving equations.
Very much difficult, you are saying? Try using moment equations first. Okay. For individual components, there are 4 components, so you get 4 moment equations, and if you strategically use those 4 equations, it would not be that much complicated. So smartly choosing the sequence of solving, okay, can reduce a lot of effort. So you can go ahead with moment equations for each member, and that would actually help you a lot. Okay. So for example, if you take this member, okay, no, yes, let's say GFD you take, okay, and then try to get the moment about F. So the forces involved would be at G and that at D. Okay. Then take the member E, D, and B, then get the moment with respect to E. So again, the forces involved would be the forces at D. Okay. So so in this way, you can see you are only taking the force at G and D in 2 equations. Of course, those are 3 variables. Okay. But then when you switch to the other half, then you have the force at G and at C. And at C, there are 2 components. Okay. So, but G you have already considered in the previous set. So you see there would be only 2 additional unknowns. So 5 unknowns. And then you can write other 2 moment equations. So 4 equations and 5 unknowns. So from that you can actually um, you know actually be able to solve at least part of them. Okay, if not, you will be able to solve them. You will be able to have expressions to substitute them in the remaining set of equations. So consider those four moment equations first, and you can take that about E and about F. Okay, so try to solve it strategically. Okay, and then we will discuss in the next class. Okay, if you find it difficult, then we can discuss in the next class.
Sir, I think one dimension should be given, right? Yeah, in that figure, we have to think that C and A both are in the same line.
C and
Because,
A,
yes, sir, the height is not given.
height of A with respect to C.
Yes, sir.
Okay, see, the fact is the coordinate of A, the y coordinate of A is immaterial, because the force that is being applied at A is along y axis. So every time you try to get the moment of the force at A with respect to any point in the universe, okay, you will never need the y coordinate of A, because the force itself is along y axis.
Oh, yes, sir, I got it.
Okay. Okay, so just keep your try your hands on this problem. Okay, acha. Now let's look at the first problem right here. Of course, it is in British system. Okay, in this problem, can you identify the two force member? There are actually three two force members. CE is a two force member, ED is a two force member, and AB is a two force member. Okay, so, and this entire problem is symmetric. Okay, which means whatever happens to FAD happens to CBG. So this is not even a problem on frame. This is just a problem on a single rigid body, which is CBG. Now the block weighs 800 lb. Okay. Now, of course, 400 lb of that would act at A, and 400 lb of that would act at G. But you see, whenever you are trying to grip something and pull it up, you are doing it by means of friction. Okay, and friction force cannot exist without a normal force. So of course, in addition to having this tangential force, which would be vertically downward. Okay, so all I'm saying in this problem, okay, in this problem, if I, let's say, draw the free body diagram of this member right here, okay, which is C, B, and G, and I'm not drawing it very nicely, but you should, and you should provide all the dimensions. Okay. And the reaction at C would be directed towards E, and that point is at a height of 12 inches and at a distance of horizontal distance of 18 inches, which basically gives you the direction of C. Of course, the force at P is horizontal. Okay. Now, this is, let's call it By, or you can simply call it B. So these are your two unknowns, the force C at C and force B at B. And of course, in order to be consistent, you need three variables. Okay, that is the mathematical part of the problem. The physical part of the problem is that that this block, okay, can only be lifted from ground by applying some normal forces. I know that the tangential force must be 400 lb, and that simply comes from the equilibrium of the 800 lb block. 400 and 400 and some normal force here, the opposite normal force there. Okay. But then there should be some normal force also. And that makes up for the three unknowns in this problem: N, B, and C. Okay. And all you have to do is solve for this. Okay. I mean, you can figure out the point of intersection of these two forces, which may be at O, and try to get the moment of the two forces at G with respect to O, and that itself will solve N, and then you can, write the force equations and solve for B and C. Okay. So this problem is not very difficult. Okay. Now I showed two aspects why there should be a normal force. First of all, there cannot be a friction force, without which you can grip an object. Okay. You cannot grip an object. That is a physical aspect. The mathematical aspect is there has to be one additional variable, otherwise the system just is rendered inconsistent. Two unknowns and three equations of equilibrium for this rigid body. And why does that physical aspect and the mathematical aspect coincide? It's because you are only being presented with optimally constrained problems. Okay. So don't fear about, statically indeterminate problems or inconsistent problems or problems without having equilibrium. Okay. Because, you need to know about all of this, that there might be such situations. Okay. But you should not be bothered about them because you will always be given optimally constrained problems. Okay. So I guess you can very easily solve this problem. It's not a difficult problem. Okay. The one which could be confusing is that wire cutter right there. Okay. So try solving all of these problems. Okay. And if you have any issue, we can discuss that on Monday's class.
Sir,
Yes.